Hello, everybody. After spending several days in a rural environment where I cleared my head and rested properly, I'm back with a new video, and this time it will be about screen reading shaders that we will use for post processing our game scene. Let's get to work. We've shown how a canvas item shader works for 2D, a spatial shader for 3D, and this time our goal is to create a shader for the entire screen to implement some post-processing effect. For example, we might want to blur the screen, convert it to black and white, simulate an old CRT monitor, and so on. Fortunately, Godot is quite helpful in this regard because it can automatically create a so-called backbuffer copy of the screen that we can use as a regular 2D texture in the shader. We'll demonstrate this with a simple trick of flipping the image upside down. But first, we need to prepare the shader itself. Let's right-click the shaders folder, create a new resource of the type shader, and we'll call it screen GD shader. Okay. Then we need to prepare the 2D component to host the shader on the top of our 3D scene. Let's create a canvas layer in our root node, a child node, canvas layer, and with a child node color rect. Add child node color, here it is. Okay. We'll open it in the inspector and find in the layout anchor superset. We'll set to full rect. So when we open the 2D screen, it is already here as a white rectangle. Then we'll open the material property in canvas item, create a new shader material, click the material and drag our new shader, screen GD shader, into this property. Good. Let me enter the code. I'll double click the shader here and it opens in the shader editor. And I will enter the code first and then I would explain it. So first we need the screen texture here, uniform sampler 2D, as it's a 2D texture. We'll call it screen texture and give it a hint, screen texture. This is just a hint for Godot to use the backbuffer copy I mentioned before. Repeat disable and filter nearest. I'll get to these parameters in a while. Okay, and now the fragment function. Okay, so delete this line. And let's set the color. That's all we need right now. We use the function texture that just takes as parameters our texture. We import it, a screen texture, and we need to flip the pixels on the y-axis. So we just reuse the screen UV for the x coordinate and flip it for the y coordinate, y and semicolon. Okay, it shows an error because, as usual, I forgot to set the right shader type. It's not spatial, but of course canvas item. Sorry about that, and now it should work. As we can see, everything on the screen is flipped upside down. Now, to explain that, you might be wondering why I wrote screen texture in uppercase letters. The reason is that this is how the same backbuffer texture was used in the previous version of Godot, that is Godot 3. So if you want to modify a shader written for Godot 3, in many cases you can simply insert this line and the shader will start working on Godot 4, at least in terms of reading data from the back buffer texture. As for the rest, I believe Godot has a page in the official documentation about the differences in shader syntax between version 3 and 4. So, uniform sampler screen texture is probably clear. It's an input parameter of the type 2D texture. What about the other parameters? Hint screen texture means that in our shader we'll use a copy of the entire screen of the window in which the game is displayed. Repeat disable probably isn't necessary here because the screen won't repeat when it fills the entire viewport, but it doesn't hurt to have it here in case we later decide to apply the shader to a specific region. And filter nearest. Filtering is used if we want a precise one-to-one representation of pixels as we see them on the screen. So let's start the game to observe the effect. Yeah, definitely upside down and much more difficult to control now. Okay, that should be fine. By the way, did you notice that our debug overlay was affected by the shader as well? If we don't want this, we have a simple solution. We'll create another canvas layer, here, canvas layer 2, and set its layer index to some higher number, for instance 10. And let's drag the debug overlay as a child node of this canvas layer. Let's run the game again. Oops, something is wrong. What happened? Yeah, sure, we changed the location of the debug node, so it is no longer referred by this string. Let's do it again. This is correct. Now start the game again. And here it is. As you can see, the debug overlay is still at the bottom left corner and can be readable as before. Good. We can perform further tweaks to our fragment code. For example, set everything to shades of red. So let's get rid of this, and we will create a new vector 4 for the color that would first take the texture as usual, screen texture of course, and the second parameter is screen UV, because this time we will not do any we won't do any transformations of the pixels themselves, just filter the colors RGB, and let's multiply that by vector 3 for the RGB components of the color. Let's make it red. This is the first component, and green and blue would be 0. And of course we need to add the alpha value. Let's keep it at 1 and semicolon. If we switch to 2D view, you can see it's perfectly green. Red, of course, sorry. Or we can use the fragment coordinates to generate a color gradient. So we will keep it right now, but instead of a static red color, we will use the coordinates again. Screen UV dot x, and we already have some kind of a reddish gradient here. Let's make it a bit more interesting. Screen UV dot y for blue, and inverted value of screen UV x for green dot x. Yeah, that's nice. Okay, now it's probably a good time to explain how the shading language works with coordinates and what's the difference between frag coord and screen UV. Let me explain. So record XY is related to viewport pixel coordinates, which means that 0, 0 is in the top left corner, while the screen width and height, for example, 1600 by 900 is in the bottom right. There is also a Z value, which is used for the depth, but we don't use it in our shader because everything is in the plane, so we'll just resort to record XY if we want to. On the other hand, screen UV, it is, I would say, normalized, which means that the coordinates 0, 0 start at the top left corner, while the bottom right is 1, 1, and everything between that is just in the range 0 to 1. Alright, enough theory. Let's dive into a shader that will significantly enhance the space shooter we've been creating before. When we defeat a boss, the explosion will create a shockwave that traverses the entire screen to highlight our success. In fact, I already implemented this feature in the sample GitHub project, so if you clone it and import it to your Godot 4, it should work. But why does it work? Let me explain every step. Okay, so I will create a new shader here. Right-click, create new resource, shader, and call it Shockwave. Alright, and it seems I created spatial again, canvas item, of course. And let's replace the shader in our material. Correct, material is here, shader. So I will drag the Shockwave GD shader. Okay, so, sorry, I will just copy this line. We'll use the depth the back buffer again, and we'll be working on a shockwave, which means it must originate somewhere, and we will create a uniform variable for this center of the explosion. Uniform vec2 center is, let's say, we will make it in the middle of the screen by default, 0.5, 0.5, and it already appeared in our shader parameters to modify. Okay, as for the fragment, let's start with defining our fragment UV parameters, which are, at least at the start, equal to the screen UV, like we did before. And what we need to do now is to create so-called of a displacement, which is basically just the difference between the vectors. Like the first vector is the center and the second one is the particular pixel. It will be used for some kind of a lens effect that is just typical for the shockwave. So I'll create another vector. Displacement is frag UV minus center. However, the longer is this distance from the center, the bigger would be the, I would say, the vector difference. But we are only interested in the direction. So let's call a normalize function that will just change the total length to 1. That's all we need to define our color now. Again, texture, screen texture, and frag UV minus our displacement, semicolon. Okay, as you can see, it seems to be too powerful, like everything was just pushed away, everything except this text remains. So let's multiply the displacement value by some multiplicator, small float. Let's try 0.05. That's better. Now we have something here. But as you can see, the displacement appears as an ellipse because our viewport is not a square but a rectangle. However, we would like to have a circular shockwave regardless of the dimensions of the active screen. Fortunately, there is a simple solution. We will use the built-in variable screen pixel size to calculate the aspect ratio, and we will incorporate the result into our algorithm. So let's do it here. Float aspect ratio is the ratio, x divided by screen pixel size y. And now how we can use that? Let's define a new vector that we will call, let's say, aspect uv, which equals 2. And of course, to calculate it properly, we must first, we don't want to apply that to 0, 0, because that's in the corner. We want to do the calculation in the middle. So instead, we will subtract from fracuv vector 2 that has 0.5 for x coordinate, and y coordinate stays 0 because we will be recalculating only the x coordinate, the longer one, divided by vector 2 aspect ratio for x, and nothing changed for y, for y. And of course we need to get back to the original point we were before, vec 2, 0.5 and 0. Okay. And of course we need to use this new value in our function. So for displacement, instead of fracuv, we'll use aspect uv. Nice. Let's convert the multiplier to another uniform variable. I'll call it power. Uniform, it's float, power is default value 0.5, and we will replace it here. Power. So a new variable appeared here. If we change it, we can see the effect in real time. Notice that if we set a negative number, the result looks like a black hole effect. Everything's been pulled into the center. This could also be utilized in the game. So let's get to 0.5. And let's say the basic effect is implemented, but it doesn't look like a shockwave. We would prefer to display something like a ring simulating a propagating shockwave, while the inside of the circle returns to its normal state. So let's start with a simple circle that can be defined by a distance of the particular pixel from the center. I will put it where? Here, for instance. Float circle is length of aspect uv minus center. All right. However, we would like to apply a gradual transition from black to white at the edge of the circle. For this purpose, the smooth step function is best suited, which works, mathematically speaking, as cubic interpolation after performing the clamp operation. First, we'll define two more uniform variables to set the circle size and the edge sharpness. Let's get back to the variable section and add uniform float size. Default value would be 0, because when the shockwave emerges, it should be just a point. And uniform float sharpness, we would start at 0.1. Now we can apply the smooth step function. So the float circle, we will add smooth step, and it takes 3 parameters. The first one would be size minus sharpness. Basically everything lower than the initial, and then this parameter would be black, would be equal to 0. Now everything bigger than the second parameter would be equal to 1, and everything between these two variables would be smoothly transitioned in some kind of cubic function I'm just showing on the screen. So yeah, let's see how such a circle looks. The easiest way to do that is just display it as a color. So vec4 circle for all components, and alpha is 1, semicolon. And of course we have to increase the size to see something. Let's do that. And the circle is here. But we would like to invert the colors, as the effect should start in the center while the rest of the screen isn't affected. Let's do it. We will just do this one minus the smooth step. There we go. So this is the circle. To turn it to a ring, we need another circle, a smaller one, and multiply our previous code by that. Let's define a thickness of the ring as a new uniform variable. Uniform float thickness would start at 0.1 again. And complete the calculation. So we will rename this circle to outer and create an inner version. Let me just copy this line. Float inner is this, but this time we need to subtract the thickness as well. Minus thickness here and here. Okay, outer, inner, and we will call the result as a ring. Float ring is outer multiplied by inner, and we need of course to replace it here. Ring, ring, ring. There we go. So let's simulate the Shockwave effect by changing the value of the size parameter again. Let's get back to 0 and boom. Perfect. Okay, let's remove the last line. And we can see it in our screen, but of course to apply that we need to multiply the power with a ring here. I mean the displacement. Okay. Yeah. Changing and explosion. Right. That's precisely what we want to do. Okay, I think we've finished our shader code, but it's not animated just by itself, so the second part of the effect will be implemented in GDScript. Let's do it. First, we need to access the color rect, as the shader material would be modified through its material. I'll drag the node to the code while holding the Control key to generate the full declaration. Let's switch to script, dragging, holding Control, and here we go. And let's make sure it's not visible by default. We'll add this line to the ready function. Color rect visible is false. We proceed with implementing a new function called Shockwave that would be invoked when the boss enemy is destroyed. Let's scroll down and find where it is. here on enemy destroyed. So here, if enemy is in group boss, we will call Shockwave. And we need to pass the enemy coordinates, so the shader would know where to start. Okay, let's define this function. Func Shockwave, parameter enemy, and let's start with pass. We will add lines and explain them at the same time. So now it's necessary to solve the problem of projecting a 3D object into a 2D plane to obtain the coordinates of the center of our effect. For this, we already have one function from before that we use to create traces for the flying bullets, and it is in the class Game Manager. So let's just reuse it. Var projection is Game Manager, and it's called 2D. The parameter would be the position of the enemy object. Alright. However, these coordinates are given in pixels, and we are working in our shader with a normalized scales from 0 to 1. It's necessary to divide the obtained values by the dimensions of our viewport. So what we need to do now is to divide it by get window and the property size. Okay, but I think that if we start that, Godot won't be happy and throw an error, because this function returns a vector 2, while this parameter is of the type vector 2i, integers. And since Godot doesn't support implicit casting yet, at least in Godot 4.1.1, we need to do a casting ourselves. So I will just change this result to vector 2. There we go. And let's set the coordinates to the shader. So first we need to access the material, correct, get material, and material set shader parameter. Parameter is called center, and the value is just our projection. So we have the coordinates and we can proceed with activating the shockwave. Let's make the correct visible. Correct visible is true. And we'll create a tween to animate the size property of the shader. Let's set the target value to 2.0 and perform the animation in 2 seconds. So first we need the tween object. Tween is get tree, create tween, and tween property, sorry, wrong arrow key, tween property. The object is the material and the property would be size, but to make sure that we call the right name, let's do this trick and just drag size to this, and it was too many quotes, sorry. Now it's correct. Shader parameter / size. This is pretty useful if you are not sure what is the exact string to call the particular parameter, so just drag it there and you should be fine. And other parameters, as we said, the target value would be 2 and the length on animation would be 2 seconds. Alright, finally we want to hide the correct again after the effect is completed, so we will add a callback to the tween callback and call function hide shader rect, and since the function doesn't exist yet, we'll add it. Func hide shader rect, and it would simply just return the initial value of the color rect visibility, which was false. Okay. Let's start the game and test the shockwave. I will also try to press the R key, as you might remember from our previous video when we will be implementing the slower time, to see how the shockwave works in, let's say, bullet time, if I'm fast enough, of course. Start and destroy the boss, which shouldn't take too long. I get this missile and fire it. And let's observe the whole integrity. When it gets to 20, I will press R. Now. And the shockwave. Have you seen that? I hope you did. Of course, you can play with the parameters to make it slower, or make the ring thicker, or do anything else just to ensure that the shockwave is exactly as you want it to have it. Okay, I tried again, and this time I slowed the time much faster than before. Let me just show you the end of the gameplay. And that's all I wanted to show in this video. I hope you liked the shader and you'll find a use for it in your project. If you are satisfied, I would greatly appreciate every like, subscribe or comment. Take care and see you in the next video.